I have been doing some work, both kind of just open source work and also work with Lightbend on Scala 2. And just recently I've started working, not full-time, but consistently with Martin's group at EPFL on Dotty, which will, in the fullness of time, evolve into Scala 3. Which, of course, doesn't mean that anything that I say here commits anybody to anything actually landing finally in the language. But I think there are good chances that it will. Okay, so I'm going to be talking about adding kind polymorphism to Scala. So a good place to start is to actually say, well, what is kind polymorphism in the first place? So it's a form of parametric polymorphism. So we're used to parametric polymorphism in the context of simple polymorphic types with type parameters. Given a polymorphic type list of T, we can substitute for T particular instantiations of that type. So we can have lists of ints, we can have lists of strings, lists of booleans. And in this kind of case, we say that we talk about the kind of the type parameter. So here we would say that T is a type of kind star. That's the jargon for it. But suppose we have a type parameter which has a different form. So instead of being a simple type parameter, in this case, for a functor, we have a type parameter which itself takes type parameters. So here, you would instantiate a functor, rather than with a simple type like int or string or whatever, you'd instantiate it with a higher kind of type, like list or option or vector. And here we say that f is of kind star, arrow, star. And the sort of the intuition behind the stars and the arrows here is that in this case, you kind of think of this as being sort of a simple type. If you were working in a dependently typed programming language, that would be basically a simple type value, I guess. In the case of a type of kind star, arrow, star, the sort of intuition is that these things are sort of a bit like functions. So if you apply list to int, thinking of list as being like a sort of a function at the type level, then you get out the resulting type list of int. So it gets so the intuition is that we have a function of some sort here. So these are two examples of kinds. So, well, what about the cases where we want to be able to abstract over the kinds? And here are some examples. So this is an example from the Scala 2 reflection library, where we have this idea of a type tag, and a type tag is a sort of a reified witness, a value corresponding to a type. So, and you would use this in the context of Scala macros or Scala runtime reflection. So you have a type, and you want to have some kind of concrete value that you can inspect and pattern match on, something like that. Okay, well, type tag, we'd kind of like to be able to refer to a type tag for types of various different kinds. So it'd be nice to have a type tag for int, a type tag for list, which is a type of kind star, arrow, star, and also a type tag for maps, which is that has a map type constructor takes two type arguments. So that's yet another kind, star, arrow, star, arrow, star. Can we substitute? Oops, excuse me. Can we substitute types like that into the same position in the type constructor? Well, the answer is no, we can't. There is literally nowhere in a Scala program, there is no way of signaling in a Scala program that a type variable can accept type arguments of different kinds. Basically, any declaration of a type parameter is completely fixed. It's monokinded, I guess. It can only have, there is no polymorphism over kinds at all. So Haskellers can do this kind of thing. So here is an example of, it's similar-ish, or it's related to type tags in a way. So this is Haskell's typeable. And again, this is a way of kind of reifying a type. And with polykinds, the polykind GHC extension, you can do precisely what we're trying to do. So you can see that we have a type parameter T for typable, and we can produce instances both for int and also for the list constructor. So we have there instances for in the first case int type of kind star, and for the list constructor we have an instance for a type of kind star arrow star. Okay, so that's kind of setting up what it is, and sort of some perhaps not yet particularly convincing examples of why you might want it. What are those reasons, really? What do they boil down to? Well, in this case, it boils down to boilerplate elimination to a very large extent. So we could, this is the same polykind definition we saw before. An alternative to that, which doesn't rely on kind polymorphism, would be simply to have a family of type constructors, sorry, a family of type classes in this case, each which support are indexed by types of different kinds. So we have typable 1 for types of kind star, arrow star, and then and then ... Obviously, the ... should be kind of ringing alarm bells of some sort or another. So again, this is another Scala example. This is a situation where the workaround is actually not very nice, and in fact is quite error prone. So rather than providing, so typeof is a polymorphic function as part of the Scala reflection toolbox, and basically this is a mechanism one would use to get hold of an instance of a reified type. So suppose I want to get hold of the reified type for list, the list type constructor. Well, I can't actually write that, so the last line is what I want to be able to write. But because the type argument of typeof is of kind star, that's not allowed. List is of kind star, arrow star. So what you have to do is a number of workarounds. So you might sort of pick some arbitrary type to plug the hole in the list type constructor. So if I get the type of list of any, that will give me the reified type for a fully applied type. So it's kind star, that's fine. But then I have to remember to kind of like poke out the type parameter to actually get hold of the type constructor. The case that looks sort of superficially more plausible is to use the sort of Scala's underscore kind of existential type syntax. Well, that's kind correct, but it's actually going to give you the wrong type, because it won't just give you the type of the list type constructor. It will give you the list type constructor wrapped in a rather complex existential type abstraction, which again is the wrong type. And you would have to do something in addition to extract the actual type constructor out of that resulting type. So both of these two things, I mean, it's incredibly error prone. I mean, I have seen and written lots of sort of Scala metaprogramming code which does this stuff wrong and forgets that the middle case is really an existential type, or forgets to kind of knock out the type constructor in the first kind of case. Okay, so. Are those examples, are those really that compelling, though? And is that boilerplate really that bad? And I kind of think for the examples we've seen so far, I think it's not really that compelling, and the boilerplate really isn't that bad. So maybe we can come up with a better example. Okay, so Shapeless is a generic programming library for Scala that I've been working on for the last number of years. It allows algebraic data types to be manipulated in a very general way via a generic representation which can be worked with at compile time rather than making use of runtime reflection. And it does this using, it's not a metaprogramming library, it is a programming library. In other words, it doesn't the mechanisms for generic programming using this library are within the language rather than escaping out to sort of meta-programming facilities. And the mechanisms it does that are the kind of the bits of Scala that sort of verge in the direction of dependent types. So it uses path-dependent and singleton types, and it uses makes fairly heavy use of induction, sort of type-level induction encoded using Scala implicits. And these are the kinds of things that sort of push Scala in the direction of, in this particular style of programming, of having a feel of a dependently typed programming language. It has a few Scala primitives which are written as Scala macros, and for the purposes of this talk, there's really the main one we need to talk about here is the generic type class. The generic type class itself it's simply a standard Scala encoding of a type class, a trait indexed by a type parameter. The macro part of it is just simply the mechanism for providing instances for this type. So the idea is to use this generic representation to take you from the world of your algebraic data types into a world of a generic representation which can be manipulated at compile time using type-level programming techniques. So for a generic of a given algebraic data type, you will get back a computed representation type. In the case of sort of product-like types like tuples or case classes, you'll get back a generic representation which is an H-list. You can think of as being sort of nested tuples. In the case of Scala's equivalent of say a Haskell data type, the sort of the sealed trait, which is the actual data type in that case, is represented as a coproduct type, or could be thought of as nested ithers. So that's our representation, and then we have just a pair of sort of projection methods. One which will take an instance of an algebraic data type to its representation, and one which will take you from the representation back to the algebraic data type. So, as I mentioned, there's an implicit macro which is part of Shapeless, which will provide instances of generic when they're needed, and Shapeless is a toolkit for doing stuff with these things. So here's an example of how you might glom a pair of product types together using generic. So if essentially we can in a very general kind of way stick two products together to create a larger product, and then inject that back into a different product type. So this is the kind of thing you can do, and this is fully statically type checked. There's no runtime reflection involved in this. GHC's generics feature is quite similar. The sort of generic type is very much inspired by GHC's generics, and you can do similar kinds of things with GHC's generics. Okay. So Shapeless initially only represented types of kind star, so fully applied complete types, so option of int, option of int, but no type constructors. And you can see that directly in the type parameters and the way they're used. So you can see that G here, it has the kind of parameter signature of a type of kind star. Similarly for the representation type. It does an awful lot of work, generic for types of kind star. A lot of the sort of standard cases for generic usage, particularly things like sort of type class derivation for type classes which are indexed by types of kind star. So lots of codecs and simple type classes, show, EQ, that kind of thing. And it does cover a lot of ground, and it's very useful. However, it's not everything. There are lots of interesting type classes which are indexed by types of kind star, arrow, star. So, for example, types like list or option, and to handle cases like these, Shapeless acquired a second generic type class, generic 1. Generic 1 is, rather than being indexed by types of kind star, is now indexed by kinds of kind star arrow star. So we have an algebraic, our G is now an algebraic data type with a single type parameter, and our representation type is, again, either a product type or a co-product type, but which has a single type parameter. And again, we have sort of a from and to, which you can see now, compared with the previous version, our from and to now have to become polymorphic because the values themselves are of types which are themselves parameterized. And this gives you a really interesting new class of type classes, which then it becomes possible to derive automatically. So, for example, we can derive instances of functor, foldable, traverse, all of those kinds of the usual tower of functional programming type classes become accessible with this lot. And if people are interested in seeing how this is done, there is a project which is part of the Typelevel ecosystem called Kittens, which kind of works through a whole bunch of these things relative to the cats library. So if you're interested in looking at that kind of stuff. Okay, I'm actually going to skip the demos. I may come back to them later if there's time. So we've got generic and we've got generic 1. Why stop there? I mean, that doesn't exhaust the kinds available. I mean, can we stop there? I mean, it feels very, very, awkward to have this bunch of special cases. Now, admittedly, types of kind star, it's kind of obvious. Types of kind star, arrow star, we've got a whole bunch of familiar type classes that we know fit into that model. But there is this sort of hint, at least there's a suspicion, at least there always was a suspicion in the back of my mind, that the reason we're not seeing many examples of doing interesting things with types of other kinds is because maybe the resources to do things with them just aren't there. And if we had resources, maybe we'd find new things. But then the other issue is that actually Scala has many more kinds than, say, a language like Haskell. Every single time you see a variance annotation on a Scala type parameter or a bound of some sort or another, that's generating a new kind for you. And it's very, very common in Scala code to end up either puzzling over how to apply type constructors which have the wrong kind of variance or the wrong kind of bounds, and you end up with duplicating signatures to work around the fact that there is no ability to abstract over variance or abstract over bounds, or at least there are mechanisms, but they're very complicated, and if you start working with them, you will quite often run into compiler bugs of one sort or another. So it feels unsatisfactory. Here's an example of something. So this is functor k. I'm not quite sure if that's in cats yet or not, but it's certainly been proposed as one. It's sometimes known in the Haskell world as a higher order functor or an H functor. So it's basically a functor, but but the idea is that instead of mapping over mapping a function over a container of t's, you map a natural transformation over a container of f of t's. So, sort of an example here is suppose. I mean, I'm sure most people doing any kind of doing anything other than hacking on compilers has had a situation where they have to deal with data structures which are incrementally populated. So, for example, if you're populating a form in a web interface or something like that, you'll have an idea of, say, in this example, an order. It's an item and a quantity. An item is a string label. Quantity is an integer. As you're sort of incrementally filling out the form, you might be in a situation where you've got the item name, but you don't yet have the quantity. So there are many ways of sort of modeling this sort of partial data problem. One of them, I believe it's more popular in the Haskell world than anywhere else, is to represent things with what's known as an F algebra. And the idea is basically to sort of thread a type variable, a type constructor through your data structure. So instead of just having an order which contains a string and an int, you can have an order of F which contains an F of string and an F of int. And the trick here is that to have your partial order, you instantiate order F at option. So that gives me an order with optional items and qualities. But when I've got a complete order, I want to sort of map that into an order of ID. So that's the identity type constructor, which takes T onto T. So that would give you an item of ID of string, which is string, a quantity of ID of int, which is int. So the idea is we sort of partially build out our data structure by filling in options, and then we can map a natural transformation which takes us from option to ID, assuming we have, actually not option, you need an option with a default or something like that, which would, but anyway, the idea is roughly to apply a natural transformation to take us from a partial order to a complete order. And this is actually a really nice pattern. It's particularly nice if you could work out how to automatically derive the implementation of func to k for an arbitrary data type. And in fact, it turns out that you can do that. But what about the kind? What about the kind? Well, the kind is not any of the kinds that we've actually seen up till now. It's not star arrow star. It's star arrow star arrow star. And then once you observe the fact that every time you it's not just sort of a question of sort of the arity of your type constructor. The type constructor itself has type parameters which themselves can have different kinds. So you end up with this zoo of potentially interesting type constructors. I mean, okay, even if we're just extending the number of star arrow stars, obviously we have an unbounded number, but the sort of proliferation, the branching structure makes it actually really quite hard to come up with a small manageable set of special cases that you're going to handle. If it's just linear, you can pick an arbitrary number and stop there. If it's a sort of branching structure, then it becomes a lot more difficult to work out what you're going to do. So I kind of think that examples like this motivate trying to do something a bit more sophisticated. Okay, so anyway, problems then. So we end up with this. If we're just going to go down the route that I've explored up to now in Shapeless, then you end up with this sort of proliferation of generic X. It could be 1, 2, 3. It could be a number of different sort of forms of the kinds here. So that's kind of, I think, just bad intrinsically. Next problem is that .E, which will hopefully become well, which definitely is going to be Scala 3, it will take a very different approach to metaprogramming, which means that we kind of want to reduce our dependence on macros as much as possible. So ideally, what we want to do is replace generic, which is currently a type class which is materialized by macros, with an intrinsic language feature. And I think this is where the problem becomes really quite serious, because you can kind of live with sort of a bit of repetition, a bit of ad hocery in a library. But I think as a language primitive, you really don't want that. You want something which is kind of regular and uniform, and without kind of arbitrary restrictions. Okay, so can we abstract away the differences between the kinds? Is there some way that we can sort of gloss over the differences? And the answer is kind of, well, yes-ish. So the first hurdle, if you remember I mentioned, is that there is literally nowhere in a Scala program that you're allowed to put a type of two different kinds. So, I mean, there is no construct which can be instantiated both at int and at list. Not even with weird syntactic trickery. It's just there is nothing. So what we can do, though, is try and encode that by embedding our type constructors in something which captures the idea of the kind. So we could try creating. So we're going to end up with duplication, but we've sort of moved the duplication to sort of one place rather than it being everywhere. So we'll capture the idea of sort of making kinds first-class things, and then we just pack our types into them. So we can have K0 for types of kind star, which is going to take a T. We can have K1, which is for types of kind star arrow star, which is going to take a T, which takes a type parameter. So you can see how that plays out for those two cases. So we can have a K0 of list of int, or we can have a K1 of list. And ... Obviously, this is our boilerplate. This is our repetition. But if we can express all kind polymorphic type classes into all usages of kind polymorphic usages in terms of just this one encoding of kinds, we've kind of at least moved the complexity into one place, and hopefully it's a bit more manageable there. So at this point, then you have to worry about how do I apply a type of this form. We can kind of kludgily make use of GADTs to do this. So we can imagine applying a K0 of something to no type arguments, and we can imagine applying a K1 of a type of kind star arrow star to one type argument. For going beyond one, we'd have to have some sort of product-like representation so you can imagine sort of rather replacing for K2, we might have a pair of types and so on, using some kind of H-list representation or something like that. The details aren't super interesting here. Okay, so if we use that kind of encoding, we end up with something that looks like this. So this is our generic. So you can see what's going on here is that, we now instantiate our generic with the suitably sort of kind-wrapped types rather than directly with the types themselves. And then our type constructors have to our projections into the representation space and back have to work in terms of the sort of the GADT representation of type application. It looks similar to what we had before. I'm not going to show you the demo. I'll show you some stuff a little bit later on. But the conclusion is it kind of works, but it's a bit clunky. And clunky is not good. Okay, so. A while ago, it is maybe 2 years ago now, actually, sort of when playing around with this kind of stuff, Pascal Voiteau and I decided to see if we could at least get over that first hurdle, the hurdle of not having anywhere to put a polykinded argument anywhere. So the idea would be to just do the absolute minimum that we possibly could to make things a little bit easier to support in the language. So the idea is that we support type parameters which can take type arguments of any kind. We're not going to provide polykinded application, so we're going to stick with the GADT-based encoding of type application. And then we're going to use kind of Scala's standard type level computation to do all the other work that would be involved. That was included in Typelevel Scala, the last release of Typelevel Scala, which is the Typelevel's fork of the mainstream Scala compiler with a few additional features which are of particular interest to functional programming people in Scala. So comparing with what we had here, so this is the encoding, you end up with something that looks like this. So this is our generic again. You can see that we've now got polykinded type arguments. And you can see that at the use sites, we just work with the types directly rather than having to wrap them in those kind wrappers. And also note that polykinded type application is still encoded as via the GADT representation. Again, I'm going to skip the demo. I'll show some code a bit later. It's a little bit better. It's still pretty clunky. We decided it wasn't really taking us far enough to make it worth pursuing, so we parked it. But then, all of a sudden, plot twist, it was adopted in Dotty. or rather Scala 3. So it's actually more or less the feature as we implemented it in type-level Scala. Has been taken on for Scala 3. Not necessarily for the reasons that I've gone through. It actually turns out that there are some interesting sort of internal reasons in the Dotty compiler which make it actually quite useful to have kind polymorphism available. Because it's basically identical to the feature, at least on the surface, to the variant in type-level Scala, it doesn't take us any further than the last demo. However, we've got this far, so it seems like there is some mileage in actually trying to do a little bit of work on actually pushing the idea a bit further and making it actually something that you might want to use other than as a sort of internal compiler artifact. So this is very speculative. None of this has actually been done yet, but I think it's feasible, and I think it will get us somewhere interesting potentially. So this is the sort of a slightly more worked out version of. This is the polykinded generic that I encoded polykinded. Sorry, no, this is the kind polymorphic generic that I showed you previously. And below it, there is this is an instance of that for a box data type. Box is basically option. So you can see that we've kind of, using the polykinded type constructor sort of simplifies things a bit. So we've got application is a problem, and you can see that in the instance, actually, it's the application which is generating additional boilerplate. So that's these two things here. They make a bridge between the sort of the generic interface for generic. Sorry, the interface for generic, and this, which is basically the implementation specific to this box data type and its kind, which is star arrow star. So the hope would be that by supporting polykinded application, we could kind of make this stuff go away and also simplify these signatures. So the idea then would be to basically have some idea of modeling constraints on type parameters in terms of kinds. So here the notion is that given an ADT G of some kind or another, we want a corresponding representation type, so that whatever kind it has to be the same kind as the kind of G. And then if we can express the idea of a polykinded application in terms of, well, what are the complementary args to type arguments of a type of the same kind as kind G, we can express that somehow. Syntax, who knows, maybe that's fanciful, but something that effectively does that seems not entirely unreasonable. I mean, the key constraint is that semantically here, these type parameters have to match the kinds of the types that apply to them. The implication here is that and in particular instances, the number and kinds of type arguments to those two methods will be dependent on what the particular instantiation is. So for example, in this case here, for this type of kind star arrow star, it's just a single type argument of type T, but in other cases it would be something else. Yes, so in the general case, we've got something which is polykinded, so we have to have polykinded arguments. In this case, in a particular instance, we know what our kinds are, so we have to have corresponding type arguments for the methods here. And erasure is great because it means that essentially all of this stuff goes away at runtime. So, and as far as the JVM implementation is concerned, we just lose all of this stuff. In the underlying implementation, we would probably end up with something that looked a bit like the stuff that we were writing by hand before. Okay, so current status, there is as I mentioned, there's a type-level Scala prototype. There's an implementation in Dotty. We need to experiment some more with polykinded application, and then we need to go through the standardization process for this kind of stuff. That's pretty much all. I just very, very quickly, I think I've got a little bit of time, I can show you some examples of what the end user code looks like in the different cases. So this is the version with boilerplate. So this is the status quo. So in this case, you can see that we're using. Can you see that here? Actually, yes, you can. Sorry. Oh.
Just a bit low.
In that case, yeah, I'd have to fiddle around with this. Hang on, what can I do? I can do set bg equals. Is that better? Yes.
Actually, yes. Unexpectedly.
Okay, so in this instance, so this is the status quo, and you'll notice here that we're using. Actually, this isn't really going to be very illuminating. Let's call it a day. Let's go for questions. Any questions?
Well, it just reminded me of something. In Hexa, you know this language, probably.
Yeah, I've heard of it.
Yeah, well, they don't have high-rank types, and to model them, at least one library uses like phony arguments. So they have some argument X, and list of X stands for just list. So is there something, well, related, helpful? I don't know.
So there are kinds of things you can do in Scala which would allow you to model higher kinded types in a sort of more reified, well, it's not reified really because you'd be modeling, you could model kinds with phantom types in Scala, and then you could use Scala's sort of type level computation to do interesting things with that. And kind of what I showed you, that encoding is sort of like that. I mean, there are maybe other things that Haxel is doing that are subtly different from this, but you can do that. The problem with this is that it's just you just end up with very, very cumbersome encodings. I mean, they're just difficult to work with. Having this stuff as a sort of first-class language feature makes it much it seems like a fancy, complicated language feature, but on the other hand, it simplifies code from a user's point of view, which I think is always worth bearing in mind with these kinds of things. Anyone else? Yes.
And of course,
compile times are always a concern, especially with Scala and stuff like this. How is this looking in terms of, is it an improvement on the old implementations, or?
I don't think adding this kind of type system feature to Scala is not going to have either a positive or a negative impact on compile times. There are other things that we're doing in Scala 2 and Scala 3 that will help with compile times, particularly for things like sort of implicit induction and things like that. So yes, but that's separate.
Something that would be useful would be an easier way to understand where things blow up badly, and tracking down where your compiles are slow due to certain things that are non-obvious.
Absolutely, agreed. Yeah. But that's slightly orthogonal to this.
Of course, yeah.
Doesn't anyone want to ask me about Girard's paradox?
Miles, did you have a question?
I'm looking. So Girard's paradox is basic. So roughly speaking, I mean, if you look at what's going on with this kind of stuff, it kind of looks like we're talking about types of types, and you might wonder if sort of lurking away in here. There's a sort of type in type going on, in which case you end up with, if you're not careful, you can end up running into Girard's paradox, which is basically Russell's paradox in type theory. So the set of all sets that are not members of themselves, essentially, is something you end up being able to encode in type theory. So there is actually no problem whatsoever with Girard's paradox in this case, for the simple reason that the way that the Dotty encoding works, so this, when I sort of gestured at it when I said the sort of internal reasons for doing it, the way that kinds are encoded is via subtyping in Scala, which is it's kind of weird, but it actually works out very nicely. So take these examples. We've got sort of normal types, say int, high-kinded types, option, list, star, arrow, star, map, which is star, arrow, star, arrow, star. Their kinds rather, are in fact, if you like, the most generalized variant of so the most general type of kind star is any. The most general type of kind star arrow star, at least with a covariant type parameter, which corresponds to optional list, is a type function from a t to any. The most general type of kind star arrow star with a second covariant type argument, which corresponds to map, is this type function here. So the idea is to basically say that to identify kinds with the most general type of that kind. And the crucial thing, which means that we don't run into trouble with Girard's paradox, is because those types already exist. We're not creating any new types. So the relationship between a type and its kind is just sort of a surjection into the universe of pre-existing Scala types. So we're not creating any new. There's no issue with our universe of types getting painfully large and this kind of stuff. So yes.
Isn't that just sidestepping the problem, isn't it?
I may have misunderstood, but isn't that just sidestepping the problem because you just happen to have an any in the new set, in the set you're projecting onto?
Not really, because we have any anyway.
Right, but much in the same way that Haskell has bottom in Hask to
well, bottom is this. I mean, any is top.
Sorry, yeah.
Right.
Well, okay, yeah, but that kind of just sidesteps the problem of termination, right? And if you didn't have any, i.e., you had to express something, you would be.
Well, in fact, you could. Okay. I mean, perhaps. I don't think that's a problem. I mean, as far as
it's not. No, but I just feel like it's sidestep.
Well, I mean, look, I used the word sidestep here, so I'm
Oh, jeez.
So yes, I mean this is. It turns out by a happy accident that we can use subtyping in Scala to encode kinds in a way which is safe with respect to Girard's paradox. Now, if there's something else wrong with Scala's type system for different reasons, obviously this doesn't help with that. But if you assume that Scala's type system as it stands is okay with Girard's paradox, then adding this form of kind polymorphism doesn't make things any worse. Anyone else?
1 minute.
If not, we just break and grab some coffee.
Applause first.